Hello, my name is Justin Willis, and today I will be explaining how to do question number 4. Let's get started by reading the scenario. A 2-kilogram block initially hangs at the end of two 1-meter strings of negligible mass. A 0.03 kilogram bullet, moving horizontally with the speed of 1,000 meters per second, strikes the block and becomes embedded in it. After the collision, the bullet-block combination swings up. This is the picture that has been provided to us in the problem. As you can see, the bullet has a velocity of 1,000 meters per second and a mass of 0.03 kilograms. It is the only object moving before the collision, as the 2-kilogram block is stationary. However, immediately after the collision, the bullet becomes embedded in the block, thus giving the bullet system a mass of 2.003 kilograms. Part A of the problem tells us to calculate the speed v of the bullet-block combination just after the collision. Here's how to work the problem. First, you apply the conservation of momentum, and 2, you solve for v. The conservation of momentum tells us that for a collision occurring between object 1 and object 2 in an isolated system, the total momentum of the two objects before the collision is equal to the total momentum of the two objects after the collision. We can apply this to solve for v. By setting the momentum of the objects before the collision equal to the momentum of the objects after the collision, we can solve for v. Thus, we can replace P with m1 v1 and P with m2 v2, standing for the masses and velocities after and before the collisions. Before the collision, there's only one object moving, and that is the bullet. It has a mass of 0.03 kilograms, so that's why we plugged in 0.03 for m1. It also has a velocity of 1,000 meters per second, and that's why we plugged it in for v1. After the collision, the two objects become one, and thus their masses is the sum of each individual mass. So that's why we have 2 plus 003 as the mass for m2. And v2 is what we're trying to solve for. Once we multiply 1,000 times 0.03, we get 3. And once we add up 2 and 0.003, we get 2.003 times v2. Dividing by 2.003 will give us a rounded estimate of 1.5 meters per second for v2. Part B of the problem tells us to calculate the ratio of the initial kinetic energy of the bullet to the kinetic energy of the bullet-block combination immediately after the collision. How to work the problem. The first thing you need to do is calculate the kinetic energy before the collision. The second thing, calculate the kinetic energy after the collision. And finally, we're going to write those two in ratio form. Let's review what kinetic energy is. Kinetic energy is the energy that an object possesses due to its motion. It can be written as 1/2 times the object's mass times the object's velocity squared. Okay, let's calculate the kinetic energy before the collision. Before the collision, the only object moving is the bullet. So we're going to use the bullet's characteristics when we're solving for the kinetic energy. The mass of the bullet is 0.03 kilograms, and the velocity of the bullet is 1,000 meters per second. Multiplying 0.003 times 1,000 squared will give us 3,000, and multiplying that times 1/2 will give us 1,500 joules. Thus, 1500 joules is the kinetic energy of the system before the collision. After the collision, there's only one object moving, and that's the combined sum of the bullet and the block. Thus, we will use 2.003 for m. And we calculated in the last part of the problem that the velocity was 1.5 meters per second. So we will plug that in for v. Squaring 1.5 and multiplying it times 2.003 will give us 4.50675. Multiplying that times 0.5 will give us 2.25 joules. And thus, this is the kinetic energy after the collision has occurred. So, now it's time to write the ratio. We have the amount of kinetic energy before the collision, 1500 joules, and we have the amount of kinetic energy after the collision, 2.25 joules. We can write this with a colon to represent the ratio form. Dividing by 2.25 on both sides will give us 667 joules to 1 joule. In other words, that means that we have 667 joules for every 1 joule of kinetic energy after the collision. Part C tells us to calculate the maximum vertical height above the initial rest position reached by the bullet block combination. How to work the problem. 1. Apply the conservation of energy. 2. Formulate an energy equation. And 3. Solve for H. Okay, let's re-examine our picture. After the collision, the bullet block combination has become 1. After the bullet has struck the block rises a certain height. This is the height that we're trying to figure out, and the height is at its maximum vertical height. We can use energy to solve for this maximum vertical height. The conservation of energy states that the total amount of energy in an isolated system remains constant over time. We can use this to solve for H. Before the collision, after the collision, we can set the total amount of energy equal to EI. And once it reaches its maximum vertical height, it has an energy of EF. Due to the conservation of energy, we can say that the energy after the collision and the energy when the block-bullet combination reaches its maximum vertical height is equal to each other, as seen here. Now that we have our equation for energy, we need to substitute the E's with actual formulas in order to solve for H. So, let's work each one individually to see what types of energy we have at each of the given positions. The energy at EI is what we will be doing first. The first thing we have to decide is if there's kinetic energy. Well, we found out the velocity of the bullet block combination was 1.5 meters per second right after the collision. So, there is a kinetic energy at this position. Secondly, is there a gravitational potential energy? Well, since we're trying to find the maximum height above the initial position, we can use the initial position as h equals 0 because it hasn't moved above or below its initial position. So, because h is equal to 0, it does not have any gravitational potential energy at that point. Now let's observe the energy after it has reached its maximum vertical height. At this position, does it have any kinetic energy? Well, if it's at its maximum vertical height, that means its velocity is going to be 0. Thus, it does not have a kinetic energy. Secondly, does it have a gravitational potential energy? Well, if it's moved above or below its rest position, that means it has a gravitational potential energy. And since this has moved above its initial rest position, it does in fact have a gravitational potential energy. Thus, we can use the fact that the initial energy has kinetic and the final energy has gravitational potential to substitute the E's and solve for H. When we substitute EI, the initial energy, for kinetic energy, we get 1/2 mv squared. And when we substitute the EF, standing for the final energy, with gravitational potential, we get mgh. The m's cancel out, and we get an equation of 1/2 v squared equals gh. Plugging in the velocity we found in part A, which is 1.5, we get 1/2 times 1.5 squared equals g, which is 9.8, times h, which is what we're trying to find. After squaring 1.5 and multiplying it times 0.5, we get 1.125 equals 9.8 h. Dividing by 9.8 will give us a height of 0.11 meters, and that is the answer to the problem.